Okay, these are a couple of problems using the Atwood machine that we talked about. So remember with the Atwood machine, you've got two masses. They're suspended on either side of a pulley. And important things we want to remember is that the pulley is frictionless, and we consider the pulley and the string both to be massless. So they don't contribute any mass to the scenario. And the tension, T, is going to be the same at all points along the string. So the way we get acceleration of an Atwood machine, we're going to use our F net equals vector sum also equals mass times acceleration. Remember, when we do this, mass has to be, the mass is added up. Okay. So my two masses, the forces acting on them. Oh, one other thing is that our coordinate system, we're going to define it as y in the direction of, it's really the direction of the larger mass, the one that's going to cause the system to accelerate, is the positive direction. So here I'm just, yeah, that's larger mass. So I'm defining this with y being positive this way. And that's just to make it easier for us to solve the problem. That way we don't have to think about it moving in y and x. We're just kind of pretending this is a y-axis that's bent, like, more or less. So my forces on my two objects, okay, are going to be on M1, it's got a force of gravity in a positive direction downwards. So we've got M1G. And then tension pulling back the opposite way. So that's going to be minus T. Okay. Then on the other side, I've got really like the opposite scenario in terms of signs. Okay. Because while this mass is going down, this mass is going up. So I'm going to have plus T minus M2G. And I'm going to set that equal to M1 plus M2 times A. And then my T's cancel out. So that's nice. That's one thing that makes this system easy to work with the tension being the same. So I'm going to take the G out because it's in both these terms. So I'll have G times M1 minus M2 equals M1 plus M2 times A. And then if I solve for A, I've got G times M1 minus M2 over M1 plus M2. That's my expression for acceleration for my Atwood machine. So this question gives us masses for M1 and M2 and asks us to determine the acceleration and the value of T, the value of the tension. So for acceleration, I'm just going to plug values in. I'm going to have 9.8 times 0.5 minus 0.25. That's just the value of my M1 and M2 over 0.5 plus 0.25. And get my handy dandy calculator. So I've got 0.5 minus 0.25 on the top, gives me 0.25 times 9.8, 2.45, and then I'm going to divide that by 0.5 plus 0.25. Oops. Hang on. I've multiplied instead of dividing. Divide by 0.5 plus 0.25. 3.3. So I got 3.3 for the acceleration. And this is always the same equation for the Atwood. Okay, so it's not on your equation sheet. It's one you'd have to memorize or get to based on the scenario. Once I have acceleration, acceleration's also the same for everything in my scenario here. So I can use that and my value, my masses, and then either one of these masses, I can plug things in to get the value of t. So I'll just use the first one because it doesn't really matter. So I've got m1g minus t equals m1 times a. I'm going to have a bunch of negatives here, but that's okay. Equals m1a minus m1g. And then if I get rid of that negative, that's going to become m1g minus m1a. And then I can just plug values in there. So I've got 0.5 times 9.8 is 4.9 minus 0.5 times 3.3, that's my acceleration. And I get almost the same answer, 3.25 or 3.3 newtons for my tension. That's funny. And I could do that with either mass. Okay, so if I'd tried it with the other one, it'd just be, the signs would be the other way around. But I have m2 t minus m2g equals m2 times a. Actually, this way would have been a little easier because I have less minuses. But it doesn't matter. You can use either one. That's another thing about this scenario. So there's my 3.2 or 3.3. Oops. So same thing. Okay, so here's a second one where they ask us for the tension. Okay, so this is, I guess, a guy pulling on a rope. So this is a 60-pound person hanging, and then a 100-kilogram mass on the other side, and we're assuming this is acting as an Atwood machine. So we're going to try and get the acceleration of the system first because we need that to get a tension value. So we've got g times m1 minus m2 over m1 plus m2. And I'm going to take m1 to be the larger mass. Okay. So this one, this guy's pulling, but this is still gonna, I think it's still gonna accelerate this way because this is a heavier mass. So this is going to be a y plus this way. So we got 9.8 times 100 minus 60 divided by 160, where I'm just adding those two masses up. And when I do that, I get 9.8 times 40 divided by 160 is 2.45 meters per second. Okay. Then again, I can use one mass for T. Okay. So I use the second one. Hang on, I'm just making sure I do this right way. I use the second one. I don't think it really matters. So I can use the first one or the second one. I'll try using the first one. So the first one's going to be, it's in my positive direction, so it's m1g minus t equals m1a. So I've got 100 times 9.8 minus t equals 100 times 2.45. Oops. So that gives me 100 times 9.8 is 980 minus t equals 245. And then I got a couple of negatives to mess with here, but that's okay. 245 minus 980. I get like 735 newtons once I clear out my negatives. And I'm going to get the same value if I use the other maths as well. So that's something you can check on your own if you want as a good practice. So, okay, those are the first two Atwood problems.